So okay, thank you very much, Luca and Ariel, for organizing this excellent workshop, and it's my great pleasure to talk about our work here. So today I will talk about the limits of the strong theory problem. This work is based on collaboration with Juan Cruz, who is now a postdoc from Odense, and also Bjorn Garbage is from a faculty from the Technical University of Munich, and also Carlos is a faculty. Violation, because it is possible to remove this term via field redefinition. And indeed, you can remove this term by chiral rotation, right? However, we have also we can have another term from the Dirac term, and in the Dirac matrix, you can have some chiral phases, and then this phases will be changed on the chiral rotation, so that actually when you perform the chiral rotation, there's a simultaneous change of the theta angle and also the angles in the Dirac masters, right? So indeed, we have a U1, and so you have an invariant which is sometimes called theta bar, and now so this parameter cannot be removed by any field redefinitions, and this is usually is called the CP violation. I mean, the normal expectation is that non-mentioned theta bar would cause CP violation. But however, physical processes are actually described by fermion correlation functions. So we cannot really discuss CP violation from the fundamental Lagrangian of QCD. So here, if we integrate out the instanton effects, then you have some effective operator, which is called top vertex. Now here again, this is you could have some complex basis in these terms, and this is our chiral basis because these two terms they have different chirality. Now the standard result of this top vertex is that in this term you have a chiral phase, the phase c equal to theta, right? And recall that in this mass term you have the chiral phases, which is given by the sum of alpha I here. So in general, when we compare these two terms, then there are misalignment unless theta equal to minus the sum of all the complex phases. Right. So this is why even after the integrating all of the instanton effects, we can see CP violation from the standard results. And sometimes, I mean, usually this term, the standard form is justified by the selection rule. So why do we call this selection rule? Because from the fundamental QCD Lagrangian, that Lagrangian is invariant under the chiral rotation simultaneously with change of the angles. And this actually the transformation for the angles, it can be viewed as a spurious transformation, right? So as a result, if you construct any effective field theory from the fundamental QCD Lagrangian, then this Lagrangian must also satisfy this selection rule. But however, the standard form is not the only option. And if you consider this this term, this form for the top vertex, and then you can find that this Lagrangian effective Lagrangian also satisfy the selection rule. But in this form, there's alignment between these two cases, and actually because of this, there should be no CP violation. So I want to remove my. Okay. Now the question is which one is correct? To determine this, we have to recompute the fermion two-point functions very carefully. And below in the calculation, we will consider only one flavor for simplicity. But in our paper, we actually considered n flavors. Before we show the calculation, I would like to explain how we obtain the standard result and why a new result is possible. So we will calculate the correlation function using the path integral. And this is the plot for path integral. Basically, you sum over all passes from the initial state to the final state, right? But if we apply this path integral to KFT, when you integrate over the gauge fields and all the gauge field configurations fall into different topological classes. They are classified by the homotopy class. And now, in each topological sector, we will see that there's alignment between the chiral phases in the Dirac master and the chiral phase in the top vertex. Well, this is the kind of so this should be very clear later. Now, if we do the sum over different topological sectors, then you kind of have the interferences between different topological sectors, and then this can give you the standard result. But however, in these calculations, usually we have a space-time volume, and usually in this calculation, you take the space-time volume limits at the last step. So this, in so doing, you can have the interferences. But now we found that if you take the space-time volume limit before summing over the different topological sectors, then those interferences disappear. So again, you get a different result, which actually you have alignment between the chiral phases in the diagonal and also in the top vertex. All right. Now we will show the calculation. So from now on, we will work in the Euclidean space-time. So here I would like to argue why we should take the space-time volume limit to infinity before sum over the topological sectors, and because this is very important, otherwise people won't believe our results. Now, so we are interested in vacuum to vacuum transition amplitude in QFT, right? Now, this is the general formula for the vacuum to vacuum transition amplitude, and in general, you are concerned with the vacuum wave function, right? So here I would like to say, so from the block wave function in quantum mechanics, you can expect that you have wave function like this. So the wave function peaks at the minima of the minima, but still it is non-vanishing away from the minima, right? But however, the usual theta vacuum is simply a superposition of the pre-vacuum. It's just the superposition for this minima. That's the wave function is vanishing away from the minima. So to avoid calculating the vacuum wave function, actually we can take the Euclidean time to be infinity to project on the vacuum. So for example, you can start it with arbitrary boundary conditions, field eigenstates. And then if you take t to infinity, then you can insert some energy eigenstates. Then this will be when t is going to infinity, then only the vacuum state transition amplitude is projected. Right. So this brings us to the starting point for the calculation. So we start some partition function. Here we have a sources for the box, and then very important thing is that inside the path integral, you have to take the space-time volume to infinity. So this is our starting point. And now, precisely because the infinite space-time volume, if you require the action to be finite, then the field strength of gauge field would be proportional to drops off as 1 over r to the cubic. And then this means that the gauge field must take a pure gauge at infinity, right? So this gives us a map from the boundary of the space-time at infinity, which is S3, to the group space, the gauge group space, which is also S3. Well, here we consider SU2 gauge theory, but you can consider any higher group which contains SU2 as a subgroup. So from this map, you have the homotonic classes characterized by the Wilding number. And in each topological class, you can find a cluster solution to the Euclidean action, to the Euclidean action, and this gives you the set point. So by the general Picard-Laplace theory, so this you can decompose your contour, your contour path integral in different as a sum of different contours. I mean, each contour passes through the set points, right? So this way, you can our full partition function can be written as a sum of the partition functions within each topological sectors. Okay. From these two equations, we can see that in each z nu, the partition function means means fixed Wilding number. Actually, you have to take a spacetime volume omega to infinity, right? This is clear from the expression partition function. Is there any question so far? I mean, because so far we have not yet go to the very technical part. Okay, let's move on. And now we need to calculate the two-point functions. This is our center target. So we first calculate the two-point functions in each topological sector, nu, so given by the Wilding number. And finally, we will sum over these topological sectors. Right? Now, for fixed nu, we will use the dilute gas approximation, which means that basically this configuration is given by n instantons and n bar anti-instantons, and nu is given by the n minus n bar. But in our paper, we actually give some very general argument based on the principle of cluster decomposition. But well, dilute gas approximation would be simple to show you the result. Now, the total two-point functions is a sum. It's a sum like this. This is basically the partition function, and this is here you the two-point functions here. Sorry, so it's quark bilinear here. Now you see that this in the brackets, the quantity in the brackets basically give you the two-point function in each topological sector, and finally you have to sum over nu. But here in this sum, you have two sums. In this sum, actually you n minus n bar is fixed in nu. And now to calculate, for example, to calculate this quantity, we need to know the Green's function in a topological sector with a fixed Wilding number. And this is actually given, can be approximated by a sum of a few pieces. So this contribution is from the vacuum. So in the field configurations, there are many parts which far away from the instanton core and the anti-instanton core, especially the vacuum, and then you have the vacuum part. Well, so near the instanton or anti-instanton, then you have contributions from the set points, right? From the instantons, and then they are dominated by the zero modes of the Dirac operator. So here by zero modes, I take the mass turn to be small so that you can do perturbation. And I'm talking about the massless, so the zero mode of the massless Dirac operator. Well, this part I think is also appears in the literature. Right. Now then we come to the correlation function. Now from this formula, sorry, from this Green's function, the step from the Green's function in the topological nu to the two-point function in a topological nu is simply doing some integrals over the collective coordinates. I mean, the instantons and the anti-instantons, they have collective coordinates like space-time position. to notice that there are two different kind of phases. The first this is the chiral phase from the contributions of the instanton and anti-instantons, and the second one is the chiral phase from the Dirac master. But here you can carefully, if you carefully look at into compare these two terms, you will find that the chiral phases are exactly the same, right? So if e to I minus I alpha gamma phi operate on PL, then it gives you e I plus I alpha, and this is precisely plus I alpha, right? And this term times PR corresponding to this term. So in each topological sector, the chiral phases are aligned. So this is very, very important. Now below, I'm going to show you that if you first sum over the topological sectors mu here, and finally take the space-time volume limit, so take omega to infinity at last. Then after the sum, you get the misalignment after the sum. Basically, you get the standard top of the sum. However, if you take the space-time volume limit to infinity before the sum over topological sectors, then you will find that the alignment persists after the sum. Well, the second option, as I have argued, spent some time arguing why we should take the second option, because, well, because we are interested in partition function, the vacuum to vacuum transition amplitude, and you have to take a space-time volume to limit to project on the vacuum transition amplitude. So now let's see how can we obtain the standard. So sorry, let's take a look again. We have sums. So for each for fixed nu, we have a sum already. But once you sum over nu, so you have two sums. And now, if you keep omega to be finite in these calculations, then these two sums just to give you can sum and bar independently, right? And if you do this, you get your function. This is from this partition function, you can infer the energy, the vacuum energy function as a vacuum energy as a function of theta bar is just a constant theta bar, and this is we are familiar with that. And similarly, you can also do the calculations for the 2-point functions. And if you do this, then you will after sum actually you will find this is our final result. And here again, you will find that this phase from the instanton contribution and this phase from the vacuum, basically from the diagonal. Yes, please. Hello? 5 minutes. Oh, sorry. Basically, so basically you find that these two chiral phases are misaligned, right? Now then in this case you have the strong free problem. Now, as we argued, if you take the space-time volume limit before sum over nu, then you can get a new result. So here we first do the sum within the fixed nu of topological sector, and then this is your result. Here you have some modified Bessel functions. Now, in the full partition two-point functions in sum over nu, then if you first take the omega, the space-time volume to infinity, then basically you have the identity. All the modified Bessel functions approach to the same value, and as a result, all these terms can be cancelled in this quantity, right? And also these two quantities can also be cancelled. And then this is giving finally our expression for the 2-point functions. So here you see that the chiral phase in the diagonal from here is basically the same as the chiral phase from the contribution of the instanton. Well, the reason is that I mean, actually the physical meaning of this quantity, the identity actually means that different topological sectors, the interferences between different topological sectors disappear if you for infinite space-time volume. So you get the alignment. Now, actually, now this is still just argue the phase, the chiral phase in the top of the vortex, right? But here we still need to think about the chiral perturbation theory to really see the CP violation. And then this is effective Lagrangian for the chiral perturbation theory. And U is just the quark bilinear. Okay, so U and you have the field U has vacuum expectation value. Basically, it is just the chiral condensate. And here the fluctuations about the chiral condensate in the angle direction is basically give you the Goldstone bosons, which are pi plus, pi minus, pi 0. And here you also have eta prime. But because the presence of this term, there's an explicit symmetry breaking of the U1, so you get the eta prime mass is enhanced. But now the problem is that in these calculations, you still have some phase C here. And the phase C is inferred and only can be inferred from the top of the vertex, right? So in our case, difference C, in the standard result, C equal to theta, the angle, in the topological term. But in our case, C equal to minus alpha, the chiral phase in the Dirac mass term. And actually, different C here would affect the orientation of the chiral condensate through this formula, right? And then finally you get from the Lagrangian, you get a term. If C is equal to theta, then you can see that actually you get a CP violation process. But if C equal to minus alpha U minus alpha D, then this term vanishes. Right? So here we consider two flavors. But if you consider S quark, then you can consider a more general case. So two options. Again, C equal to theta, CP violation, and C equal to minus alpha bar, then no CP violation. Sorry, so this should be alpha bar just the sum of the phases in the Dirac mass. Now here there's a last comment. So from the lattice case, we know that it is confirmed that there's a non-vanishing topological capability. Right? But however, our result does not really mean well. So so if the interferences of between different topological sectors disappear, then basically you are kind of working in a fixed topological sector. And then actually, if you apply the definition for the topological capability for the whole space time, you can get a vanishing topological capability. But however, if you this actually, if you consider a local capability, then it is not necessarily zero. Here you can. This is an example to show you. So so for example, this is the whole space time, and the topological charge, the value number is fixed for the whole space time. However, there's still some fluctuations for the topological charge in the subvolume. So there's a constraint that M1 plus that M2 is equal to that M, but that M1 itself can fluctuate. And we actually carried out the calculation, and we found that locally the topological capability is given by 2 kappa, and this is still in agreement with lattice QCD simulations. Now I will give the summary. So in our paper, we constructed fermionic grid functions in BPST instantons with general complex masses, and we find that so the alignment between so we observed the alignment between the chiral phases in the Dirac mass term and the Hooft term for infinite space-time volume. And we argued that why we should actually take infinite space-time volume, because we have to take the Euclidean time to infinity to project the condition function to the vacuum transition amplitude. And by the way, so in this talk, I used the dilute gas approximation, but in our paper, we actually give a more general analysis based on the classical decomposition principle. Finally, thank you very much for your attention.